Hi, AP Calculus students. So this next section, 4.2 and 4.3, we're looking at when functions are increasing, decreasing in the first derivative test. So to give you a little bit of context, we're gonna be taking derivatives, and now instead of just looking at where the derivative is equal to 0, we're gonna be looking to see when the derivative is positive, when the derivative is negative, and this is going to help us to find those relative minimums. So in previous units, we've been able to find global or absolute extrema, like the biggest maximum or the biggest minimum, but we'll be able to find the local maximum and minimum using this. So basically, if a graph exists on an interval, it is doing one of three things. It's either going to be increasing, decreasing, or staying constant. That makes sense. That's what a graph will do. So we would like to be able to interpret information about a function by analyzing information about its derivative. Since f of prime tells us the slope of the curve, y equals f of x at any point, it tells us whether the curve is going up, going down, or staying the same at each point. If we therefore know the values of f prime of x on a given interval, we know whether the graph is increasing, decreasing, or constant on the interval. So this is wonderful. It sums up this paragraph with images. So if f of x1 is less than f of x2, then f is increasing. Clearly this is increasing, which means that the derivative is positive. So f prime is positive. It's bigger than 0. Okay. Here, f of x1 is greater than f of x2. This thing is decreasing, which means f prime is less than 0. This means f prime is negative. So when f prime is negative, the function is decreasing. And then this is one that we know. If here the y values are the same, f is constant, the derivative f prime equals to 0. Okay. So this is basically everything that we've already talked about, kind of summarized in the official math notation that you've been getting a little bit more used to. So here's just the official math notation that summarizes these ideas. So you should go ahead and pause and make sure you understand what this is saying. I paused a little bit too, just to kind of remind you, you should pause. Make sure you understand this. It's summarizing up these ideas up here. Okay. I mean, this is just the same thing. It's really giving you these ideas. They just are adding this word monotonic. That just means over the whole interval it's increasing. Over the whole interval it's decreasing. So it's not changing from increasing to decreasing. So I know this is like a funky word here, but it just means over the entire interval it's going to be increasing, or over the entire interval it's going to be decreasing. Okay? Okay. So all this front page saying the same thing. Go ahead and pause if you need to digest a little bit more. Otherwise, we're going to look at a little example. So, example 1, the graph of a function f of x is defined on this interval, is shown. List the open intervals over which the function is increasing, decreasing, or constant. So remember, this thing is just f of x, it's not f prime of x. So if we want to show where it's increasing or decreasing, we really just need to look at this function. So it's increasing where it's decreasing and where it's constant. Okay. It's increasing right here, and that is on the interval. It says list the open interval, so that's why I'm using parentheses. So it's on the open interval between -3 and 1. It's decreasing right here. so between 3 and 5. And it's constant right here, so between 1 and 3. So basically the whole closed interval between -3 and 5 is completely covered there, because these are the only options we have. It's either increasing, decreasing, or constant. So here we have this little box. At what values of x can the graph of a function change its increasing, decreasing, or constant status? The graph of a continuous function can only change its increasing, decreasing, or constant status at critical points. So if, like up here, we have a continuous function, it's only going to change from increasing to decreasing or increasing to constant or whatever. It's only going to change at critical points. That makes sense. So it changed from increasing to constant at the point 1, which is right here. This 1 is a critical point because the slope equals 0. And then it changed from constant to decreasing right here at a critical point because, again, the slope is 0. So these are the critical points. And it can only change from one to the other at critical points. Oops.
Good evening, campus. This is Mr. Calderia with a reminder.
Always interrupted.
All practices and after-school activities should have been completed by 5:30. Everyone should be making a beeline for the exits. We will be closing down and securing the campus. Please make sure you have exited before that time. Thank you and have a great evening.
Yep, it's 5:45 and Miss Patterson is still on campus. So sad. Okay, so yeah, these are the critical points, which means that these are the values where it can change. For discontinuous functions, it's a little bit different. It can change from increasing to decreasing to constant at critical points or at discontinuities, which I'm going to show you down below. So up here is an example of a continuous function. Down here is an example of a discontinuous function. So at discontinuous functions, there are more locations where it can change from increasing to decreasing or whatever. So the open intervals over which, wait, here the graph of the function f of x is defined for all of x not equal to -5 and 5. So these are the asymptotes where it does not have value. So those are the discontinuities. List the open intervals over which ant walks uphill or downhill. I don't know why they made this such a baby. It's like a problem for babies, even though it's calculus. I don't know. Whatever. So the ant is walking uphill. It's increasing on the following intervals. It's increasing right here. He's walking upwards. So it's increasing on -infinity all the way to -5. And then we have a discontinuity here, so he can't keep walking up. That ant is just walking up forever, I guess. And then this ant is increasing still up until this point. So he is increasing from -5 to 0. Notice that here we had to have a break at -5 because there's that asymptote. So here they're increasing, and then we're decreasing on these intervals. So at this point, this is a little critical point. At our critical point, he changes from increasing, he's going to start decreasing now, so from 0 to 5. In union with 5, he's still decreasing. He's going to be walking downhill like that. So he's decreasing from 5 to infinity. Okay. And notice we could change, we could have changed here at these discontinuities, but we didn't. We didn't happen to. We only changed at the critical point of 0. Okay. Flip. We're going to look at more algebraic examples. So yeah, these on this page, the page we were just on, these are graphical examples of being able to tell when a function is increasing or decreasing. Obviously, it's much easier to look at a picture of it and figure out where it's increasing or decreasing, but sometimes we won't have that option. You'll have to figure it out algebraically. So without the graph, we must find any critical values and discontinuities. So remember, these are the points where it can change from increasing to decreasing to constant. And then we'll test the intervals in between them. Okay? So in example 3, it says, find the open intervals on which f of x equals x cubed minus 3/2 x squared is increasing or decreasing. So step 1 is to find critical values or discontinuities. Okay. So critical values, well, there's no discontinuities here, so we don't really need to do that. Check. The critical values are all the points where f prime of x equals 0. So we'll find all those values. So f prime of x equals 3x squared minus, take the derivative of that, is 3x. We'll set it equals 0 and solve for x. So we can factor out, zoom a little. Okay, we can factor out 3x and we get these as my critical values. Yeah, there's no discontinuities. So now we're going to test the intervals between to see if increasing or decreasing. Oops, sorry. Haha. So test the intervals between them to see if increasing or decreasing. So we're going to make these tables. You maybe remember making them before, and we're going to put our critical values on them, so 0 and 1. And since we want to see if we're increasing or decreasing, we are going to plug these values into f prime. Okay? So we're plugging these values, these x values, into f prime, the derivative, not into the original function, because we want to see what's happening to the slope. So if we plug in a number like -1 into here, if we plug -1 into here, we would get 3 plus 3, which is a positive number. Cool. So we plugged in like -1. If we plug in 0.5 into here, we would get a negative. And then if we plug a number like 2 into the derivative, we would get 3 times 4 is 12 minus 6. This is a positive number. Okay. Okay. So where this is increasing and decreasing, we just list it out. So it's increasing on -infinity to 0 in union with, so and 1 to positive infinity. And it's decreasing here between 0 and 1. Ta-da! Okay. Number 4 is very similar. Go ahead, hit pause, and try this without me. So, pause it now. Pause it now and try it. Seriously, pause it now. Okay. I'm assuming you're back after trying this example, and now I'm going to do it. And I'm going to stop talking because I'm losing my voice, so you can just follow along. So factoring. Okay, so here are my critical values. And at my critical values, I'm going to test the intervals. So if I would plug these numbers in, I would end up getting negative, positive, negative, positive. So it's increasing. And decreasing here. Did you get that? Good job. Okay. We have one more big idea. So far we've been testing intervals to see where they're increasing and decreasing. And now we're going to figure out, okay, how can we actually use these tables? Like, what information do I get using these? And this is information about relative extrema that people have been asking about a lot. So up here it says, for a continuous function, knowing when and where the sign of the derivative changes lends great insight into existence of any relative maximums or relative minimums. Okay, so this is relative is another word for our local maximums or local minimums. So remember those words local max and local min? They also use the word relative. So this is it's kind of the same thing where they interchangeably use the word global and absolute. This is the same thing. They'll interchange the word local with relative. So don't get confused if you see either local or relative. Okay, so the first derivative test basically is used to find the relative extrema, or the local extrema. So if f of x equals, if x equals c is a critical value, so c is representing a critical value, then if f prime of x changes from negative to positive at x equals c, then f has a relative minimum at x equals c. I know that the words are kind of hard to understand, so let's relate it to this picture. This corresponds with this first thing up here. So f prime, which is the slope, oh no, that's not right. It goes with this one. Sorry. So f prime changes from negative. Here, f prime is negative. And then it turns to positive. F prime is changing from negative to positive, so there's a relative minimum at c. See how nice that translates from that? And then number 2 is this one. My bad. So 2 says f prime changes from positive to negative, then there's a relative maximum, it's a maximum at c. And then 3, it's a little confusing to just read, so the pictures are super helpful. 3 says f prime is positive on both sides of c, or negative on both sides of c, then f of c is neither a relative maximum or a relative minimum. So this is like a case of a cubic. We still have a slope of 0, so this is still a critical point. That's still a critical point. But the slope is positive on both sides of it, so there is no maximum or minimum. And on this one, we have a critical point, but it's negative. The slope is negative on both sides, so it doesn't end up being a maximum or a minimum. These are kind of the options you have. And this is where the tables, those kind of like number lines we were just making, become really useful because we can see where it's increasing or decreasing, and if it follows one of these patterns, so it goes from negative to positive, you know you have a minimum. Or if it goes from positive to negative, then you know you have a maximum. Okay? Down here, this is just kind of bossy stuff to help you when you're doing free response questions for the AP test. So when you're doing the first using the first derivative test to justify relative extrema, to find, you can also think to find relative extrema, you must write a concluding statement clearly communicating the type of sign change of f prime at each x equals c. I will show you how to do this. And it said, thou mustn't use pronouns either. So basically you just need to be specific. Like, you don't want to say, don't say it changes, don't say it changes to positive. The it is a pronoun here. You should say f prime of x changes to positive. So all of my students, even my BC students, have a hard time remembering not to use pronouns. You need to be really specific because it could be talking about f of x, but we're talking about f prime of x, so be very specific with your language. All right, example time.
Good evening, Panthers. This is Mr. Galleria reminding you that we are presently shutting down. You need to be off campus now. Have a good evening.
I'm kind of afraid that I'm going to be... I've gotten locked on campus before, so I'm actually going to end this. I'm going to continue it later. I'm sure you're all going to laugh at the YouTube video when I say this. Okay, so I will show you the examples at another time.